Okay.
Awesome.
Now you have to rethink which group you want to join from now on.
You're hilarious.
Okay, so let's get started. I just want to remind you all that the quiz is on Monday. If you want to come 5 minutes earlier so that we can start early the quiz and not be behind in lecture. I guess I got behind in lecture last time because of the quiz took a little bit longer. And everything after the first quiz. So everything when we stopped, I think we were having the resolution discussion in chromatography. So start studying from resolution chromatography, HPLC until my last lecture on Monday, and then GC and MS. Yeah. So basically everything until the end of last Monday's lecture. Okay. I have 2 items today with me. One item is for participation. So you're going to get a +2 and a chocolate.
I'm not worried about that. I don't know.
And if you are somebody that participates a lot, you can grab a chocolate as you go and sit back and relax today. And I noticed several people falling asleep last time. So if you fall asleep, you're going to just see this coming at you. Okay.
You pick the one that has
Yeah, the best. Look, it's like shower. Okay. With that, we can get going. All right. All right, recap questions from last week's lecture. This is help us dive into specific UV-Vis applications today. What are the different species of matter that can be analyzed using spectroscopy?
ready for chocolate.
Okay, Michelle?
Electronic.
Okay, Michelle's not going to get a chocolate, but she was looking into her notes. Okay, so electronic, no, it wasn't even the correct answer. So, what are the species of matter? Okay, and, huh? Okay, that would be light. So what species of matter will interact with light? But anyway, here, since you are encouraging your participation. Okay, Erica?
Atomic and molecular.
Atomic and molecular. Perfect. Yes. Okay. Name the different forms of radiation-matter interactions. We have different forms of interactions. What are they? Nicole?
Absorption, emission, and refraction.
Very good. There's some of those. Hint, hint, Tara. There is absorption, fluorescence, diffraction, refraction, scattering of light. Okay. What are the spectral regions most relevant to food analysis? Okay. Michelle.
UV, visible at IR.
Okay. Sorry, fell too short. What is the difference between electronic and vibrational energy, and to what spectral region each corresponds to? So electronic excitation is due to what? Let's handle this one at a time.
Light.
Yeah, but what part gets excited? Electron. But anyway, for effort. So vibrational energy?
Is about the photon stream?
Well, what vibrates? So when a photon of light hits an atom or a molecule, does it gain electronic energy if it's a molecule, or vibrational energy, or both? Answer that, get a chocolate. Easy. Huh? Both. So vibration and energy is basically when you have a molecule and you have atoms that are bonded to each other, so the bonds will vibrate, stretch, or bend. So that would be vibration. When you have only an atom, so it would be mostly electronic energy, where your electron from shell jumps up to a higher shell, basically. So spectral region, electronic corresponds to what region? Is it UV, IR, visible? Okay, I'm gonna get a chocolate, or Andy.
Electron is UV and vibration is IR.
Yes, and electronic is also UV-Vis, so both. UV visible and vibration is IR. What's the difference between absorption and fluorescence? Yes, Sarah?
Is absorption like when it actually like takes in the energy, and fluorescence is like when the electron like goes down, its energy level and goes out?
And gives off energy in the form of photon, not in the form of heat. Ben, out of the way.
Scared.
I'm scared. What is the difference between diffraction and refraction of light? Amanda?
Diffraction is when light gets separated into multiple wavelengths,
Yeah?
and diffraction is when it just hits it and bounces off.
Or changes direction.
Changes direction.
Yeah, like the refractive index detector. Hint, hint, Ray. Okay. How does the wavelength impact the frequency and energy? That means if you have a longer wavelength versus a shorter wavelength, what would be the frequency and the associated energy, Ben?
Shorter wavelength has higher energy
And,
frequency.
and
Longer as lower.
they both want the chocolate, yeah. Okay. Let me see how far I can go. I'm having fun today. It's Friday. Close. Okay. More questions. The following is true. I don't expect you to know this, but let's see if you remember anything from physics. No. Molar extinction coefficient is constant for all analytes. A highly concentrated sample may result in deviation from Beer's law. Incident beam minus exiting beam is equal to the light absorbed by the analyte. John?
I'll go for E.
You go for E. Why? Explain.
Wild guessing.
Huh?
Wild guessing.
Wild guess. No. Any other answer with some explanation, Sarah?
I'll go with
You go with B?
yeah.
You're very brave and correct. She got 2 today. All right, so I'll explain that later in more detail, but molar extinction is very specific to each analyte. It's absorptivity of the analyte. It's like when you do when we did the PDA, and then you had a very specific absorbances at different wavelengths. So this is analyte specific, and yes, B, we saw this, maybe some of you that did the AA. I don't know if Cindy talked about that, but if you have standard, for example, for calcium, we went up to 16. We didn't do, did we go up to 20? Just 16. Above that will be too concentrated, and there will be interferences, and then you lose the abundance of Beer's law, abundance by Beer's law. Incident beam minus exiting beam does not equal absorbance, and we'll talk about that. It's a ratio. It's not subtraction, because light, when it hits a substance, it will scatter, it will diffract, it will refract. Not everything that hits your sample get absorbed or transmitted. So none of the A and C are incorrect. E is correct, and we'll go over detail as we go. Okay, another one. In both absorption and fluorescence spectroscopy, UV-Vis radiation is used. The transmitted beam is the signal measured. A grating monochromator is needed. Jesse?
C is right.
C is right.
A and C.
No. B, well, B is correct in absorption, but fluorescence, you're measuring the emitted radiation from the particle. So you don't measure the transmitted beam, you measure emitted beam by the emitted light by the species of matter. And yes, in both fluorescence and absorption you use UV-Vis, and in both cases you need a grating monochromatic. So, okay, moving on. So today is focused on UV-Vis. Next time we're going to talk about atomic absorption specifically for atomic or elemental detection. And then later on we'll talk about IR next. So for UV-Vis, mainly we're looking at absorbance and fluorescence of light. And you can use that for qualitative, for identification and determining some idea about the structure, and for quantitation. So some of the matter or compounds that you'll be analyzing will have an inherent signal. So with inherent signal, what I mean is that they can absorb light or they can emit light. So by chemically induced, meaning initially they don't absorb or emit light, and you initiate a chemical reaction and the product generated will either absorb light or emit radiation. So for example, in this case, if you're measuring amino acid composition, not every amino acid, there's only 3 amino acids that can absorb light, but the rest, if you want to detect them, you will react them, let's say, with OPA, the agent, and if you do that, you get a product that will fluoresce. If you react them with anhydrine, you get a product that you can measure absorption. So you can, there are so many different applications, and we'll have a lot of different applications as we go ahead and discuss different chapters in the semester. But for now, I'm going to give you a few examples. Quantification of macro components. You will be doing a carbohydrate lab focused on determining total carbohydrate using phenol sulfuric acid method. So in this method, you react the sugar, you break the sugar or the carbohydrate into glucose, and the glucose is converted to furans, and furans will give you color absorption, basically, that you will measure color. Quantification of microcomponents, so components that are present in small concentration. An example is the thiamine fluorometric method, which we'll talk about when we cover the vitamin chapter. And there are a lot of different quantification of microelements. What you did in AA is one example. So there's so many different examples. This is just a couple. Enzyme-linked immunoassays, or ELISAs. We use absorption a lot in ELISA because you can determine components such as allergen, mycotoxins, pesticides, using ELISA, and in there you use an enzyme linked to either your antigen or your antibody, and then you give that a substrate, and the product will be something you will measure absorbance of. So this will be a whole chapter on that later on. But just showing you an example that you use spectroscopy in so many different applications. So basically absorption spectroscopy is based on how much light has been absorbed, obviously. So what happens is you have an incident beam and then an exiting beam. Part of this light that enters the cell where you have your sample gets absorbed, and part of it leaves, and part of it gets scattered, part of it gets reflected. So we are interested in the part that got absorbed, and that's what we want to relate to concentrations. So if we look at the different letters here, C is for concentration, A is for absorptivity. So these both are related to the amount or your solute that you're measuring. And B is in length in centimeter of your compartment, sample compartment. So relative transmittance, how much relative meaning exiting beam over incident beam, and or relative absorption is what is correlated to concentration. And here's the correlation. So transmittance, like I said, is P over PO. And then if we want to look at percent transmittance, is the relative transmittance by 100. But this is not linear with the concentration. So this is not used to determine concentrations. What is linear is the negative log of transmittance, or the inverse log of transmittance, and in this case, it's absorbance. This has a linear relationship with concentration, and that would be your Beer's law. So Beer's and Lambert law. I don't know why Lambert gets dropped. It's two guys that came up with the law, but Beer's gets all the credit. I don't know why. So, but anyway, it's Beer's Lambert law. Even the book doesn't give Lambert the credit. So, not sure why. But here's what it is. It's absorbance equal absorptivity by the length by the concentration. The concentration can be in molar, millimolar, milligram per milliliter, percentage, any form of concentration. And B is the path of length that goes through, which is basically the length of your cell. And absorptivity has inverse centimeter and inverse concentration unit. So they cancel out. If you put A, B, C, then the units cancel and absorption doesn't have a unit, basically. So A, when units are in centimeter, the -1, and molar, the -1, it's often you hear the term molar absorptivity or molar extinction coefficient. These mean the same thing. Absorptivity, if it's molar, that means the unit is in molar, and extinction coefficient mean the same thing. So when you hear these terms, they all mean the same thing. So absorptivity is a proportionality constant dependent on molecular properties of the species, wavelength, or chemical environment. Jesse? A and B. Any other? Jenny?
All the above.
Why, Jenny? Can you give an example?
If there is other components in your solution that might absorb more light.
Well, if there are other components in your mixture that can interfere with the characteristic of your analyte, so might cause a dissociation, make it an ion form versus a molecular form. So yes, so the chemical environment does impact, and of course the molecular properties of the species, which makes it unique, makes it have a specific absorption, and of course the wavelength. At different wavelengths you have different absorption. So it's critical that we measure accurately absorption, taking into account other components in your sample. So there's always what you call either, if you have a reference cell, that means you have your spectrophotometer and you have a cell for a sample and then a cell for a reference. The reference will have almost everything you have in your sample except the analyte. So that would be your blank. If you do not have a reference cell, oftentimes you insert a blank and you would hit 0. You're zeroing the absorption. So you're taking into account any interferences that would come from components in your assay that might result in deviation of the absorption of your sample or your analyte. And also, you correct for any scattering of light or reflection of light. So when light hits a certain surface, part of it gets reflected. When light hits particulates in your sample, part of that light is going to be scattered and also reflected. So having a reference cell is going to correct for that. So it's very important that either if you have a reference cell, you will have your blank put in the instrument, or you will just insert your blank, zero the instrument, remove the blank, and put your sample in. You're going to do that when you do the total carbohydrate assay. You're going to have to zero your instrument using a reference blank. There are instances where there is deviation from Beer's law. We cannot always, in order to apply Beer's law, which is A equal ABC, we have to make sure that we are within the parameters that allows the law to apply. So that's why it's very important to measure in the linear range. So sometimes concentration that are too high, your solute are very close in distance to one another, so they interfere in the chemical environment of each other. So they might share electrons, bounce off electrons, for example, and that can result in differences in absorptivity. So high concentration we usually avoid in spectrophotometry. Therefore, we always tend to dilute our samples to fit with Beer's law. We talked about chemical processes. If you have molecules that tend to dissociate, lose a proton or gain a proton, or dissociate in any other form, or ionize, especially if you have an unbuffered system, then that will affect your absorptivity. Molecule versus an ion, they will have different absorptivity. And polychromatic light, meaning you don't have a light with a single wavelength. You have multiple wavelengths hitting the sample at the same time. You won't, then you are deviating from Beer's law. Beer's law, you should have a single wavelength at which you determine concentration, because you will have different absorption going on when you have multiple wavelengths hitting your sample. You cannot correlate all these absorptions to your concentration, so we have to select a wavelength for measuring concentration. There are several procedural considerations also. It's very important that if you're working, let's say, with a sample and you do not have a lot of volume in your sample, if you put your, let's say, less than 0.5 milliliter in a cuvette like that, and the light passes over it, obviously that's something you don't want to do. So there are special cuvettes that allows you to put less amount of sample and alleviates the volume up, so you can hit the light. Homogenization and clarification is a key. Oftentimes there is a clarification step, either a filtration like you did for HPLC, or a centrifugation step that allows your sample that you're analyzing to be clear. If it's turbid, that will scatter a lot of light and then will falsely increase your absorption. So if you do not have a clear sample, then measuring absorption is not the way to go to determine concentration. You have to think of something else. Always use the appropriate control, meaning oftentimes you add a lot of reagents. You want to make sure that you control for an addition of a substrate, for example, or control for an addition of a buffer. So you always measure different components that goes into your sample so that you can correct for that. So any modifying agents that are present in your sample due to the chemical assay that you're running, you have to always correct for that. Yeah, so oftentimes, and Chelsea knows this when she runs ELISA, how many controls do you have? A lot. A lot. So for every agent she adds, she creates a control. Sample holding cell. This is also important, and some people, really, this is the silliest mistake. If you're measuring UV absorption and you use plastic, for example, well, plastic will absorb UV. So you don't want to do that. You want to make sure you use the sample compartment that does not absorb light in the range that you are looking to measure. So quartz and fused silica are mostly used for UV range. Glass and plastic are used for visible range.
But you also have to be careful like what your sample actually is too, because certain samples can't go in plastic versus like glass, just like.
Yeah, exactly. Like if you have an acid, for example,
Yeah, exactly.
and that you will do in the total carbohydrate assay. You don't want to use plastic because that might melt your plastic. Yeah, consideration of course, of the composition of your sample. Okay. Other procedure consideration is how you select your wavelength. So often, like we talked about in HPLC lab, you want to select the wavelength that gives you the maximum absorbance, unless that wavelength interfere with another component in your sample. For example, if we're analyzing zinc and iron, at the same time, you have to select a wavelength that both of them do not absorb. So it's not always your optimal or highest absorbance wavelength, but the wavelength that does not cause interference, and if there's no interference, you select the maximum absorbance wavelength. So when you have, when you select a wavelength or a band, we call it a band because I'll explain why we call it a band. Remember your monochromator? It's basically you have a slit that allows a diffracted light and a single wavelength to pass. Sometimes it's not really single, it is multiple wavelengths, but very close to each other. They vary maybe in 1 nanometer or 2 nanometers difference. Okay, so that's why we call it bandwidth. Sometimes if your sample is very dilute, you don't have a lot, you want to maximize sensitivity, so you widen this a bit so you have more radiant energy hitting. So you will have more wavelength entering, but if you have here kind of a plateau where 312, 311, 313, for example, all are high, then you can allow increasing the band to increase the radiant energy going through. If that is not a problem and you have a very steep hill here, you want to be very specific and selective. You do not want to select a wavelength where there is a steep change. If you miss 1 nanometer, there will be a steep change in the absorbance. You do not want to do that. You can ask questions also. You'll get a chocolate if you want. Any questions before going on? Yes, Ben.
How do you determine your maximum absorption?
How do we determine your maximum absorption? That's a good question, Ben. And if you remember what we did in LC, okay. All right. What we did, we had a PDA, for example. We were able to scan to see at which wavelength we have the maximum absorbance, and at that wavelength we got the peak area. But if you don't have a PDA, what you will do, and actually you'll do that in one of the labs, I can't remember which lab now. Which lab was it when you measure at different wavelengths?
Isn't that the,
Is it the glucose lab?
yeah, it is. Is
Okay.
that the one where you can pop, like the Sprite and stuff?
Yeah, so they will measure at different wavelength and then they plot it, yeah. So you would measure at different wavelength and plot the absorbance, and you go, okay, so the maximum absorbance I want is at this wavelength. So, good. It's also very important to calibrate your instrument, meaning you're telling it when there is no light passing and when there is all the light passing. So you would close the light You hide the light basically, and you will calibrate it to be zero transmittance. And then you open the light and there's nothing in the cell, and you got, this is 100 transmittance, calibration. So it's very important to do that. We talked briefly about deviation from Beer's law. Beer's law, you need to have a linear relationship between the absorbance and the concentration. So, and this is very unique for the type of element or the type of molecule you are analyzing. There were, those of you that did the AA, the iron went up only to 10, the calcium went up to 16 parts per million. So it depends on the molecule or element you're measuring. You will have a specific linear range that you do not want to exceed. You do not want to quantify when you don't have linearity, when your curve is having a curvature. That means you lost linearity. Here you cannot have accurate detection when your concentration is above 7.5 in this example. So you want to make sure you do the dilutions and you have your standards to have a linear relationship. And another important thing is you want to have your lowest standard lower than what you anticipate in your sample. You do not want to make quantification where your sample is less dilute than the lowest standard. You always have to adjust, make sure that your calibration curve fits all of your data points. You either dilute your standards or you dilute your samples to make sure that they are within the linear range of, and also the threshold. You don't want to dilute too much, then you will lose threshold and you become close to the noise, what we call error or noise, which is not true concentration. This is a very confusing concept, and I'll try to go through this very slowly and carefully. Sometimes your sample matrix is very complex, meaning within your sample there are components that will interfere with the absorption of your solute of interest. You cannot generate a blank. You will not be able to have a reagent blank or a control that mimics what everything in the sample is. In this case, what you do is you do what we call standard addition protocol. Your sample becomes your part of your calibration curve. How is that? All right, I'm gonna visually draw volumetrics and go over this with you. So let's have 5 of these, and they should be equal in size and shape. You don't have irregularity like that. Okay, so you have 1, 2, 3, 4, 5. You will have your sample would be constant volume of your unknown sample. You dilute your sample and you add, let's say, 5 ml of sample in all of them. Okay? In 1, 2, 3, 4, 5 vials. And then what you do, you have your standard. Let's say you have, I'm going to say glucose, just for simplicity. You have 100 parts per million glucose solution. So you add here, you put 5 ml of standard. Here you put 10 ml of your standard. Here you put 15 ml, 20, and 25. So what you're doing is you're building a standard curve within each sample. Okay, are you following? So same sample amount, but different volumes of your standard. Then what you would do, you would run your assay, and then you plot your absorbance over your volume of your standards. And then you have an equation of the line. This is the equation of the line. K is the constant, which is the path length times absorptivity. And this is volume of your sample or standard, sorry, concentration of your sample, no, volume of your standard, concentration of your standard, volume of your unknown, concentration of your unknown over the total volume. All of these are diluted to the same volume, let's say 50 ml. Okay? So you have everything. When you plot the line, you'll have everything except the concentration of the unknown, and then you can get that. Okay? This is a complex procedure, but is probably the only procedure one would follow when you have a really complex matrix that will interfere with your analysis. Very commonly used too.
What would be considered a very complex matrix?
So if you have components in your sample that will interfere with the absorption of light, let's see. This is commonly done for phenolics, for example. If you have a sample of cereal product and you're measuring phenolics, your cereal component, there's so many different constituents in that product, and then that would be one way to determine phenolics. Okay. Instrumental error, or in other words, what you hear commonly is the noise. We call it noise. So you will see, for example, when some of you did the LCMS, saw little spectral peaks, and I told them ignore that. This is noise. This is instrumental noise. So every instrument has that. Every instrument has absorbances that are false, that are noise, just from the instrument itself. For that, I'm not going to ask you because you wouldn't probably guess that, but it has to have be smaller. The noise needs to be smaller than the concentration, or not the concentration. I would say the response of your sample. So the noise needs to be much less than the response of the sample. That's why we work with intermediate concentrations. That means you don't want to have very low concentrations, and you don't want very high concentration. So typical absorbances usually are between 0.8 to 1. 1.2 is sometimes acceptable, but if you have absorbances that are 0.02, for example, this is very close to your blend, very close to the noise. So you don't want that. And if your absorption is reading 1.3, 1.4, or 2 sometimes, you are probably outside of the linear range. So you have to be very careful in selecting the absorption you want to be at to make sure that you have correct reading. So rule of thumb, we say 0.2 to 0.8 would be great. If you make sure your sample is diluted so that you get absorbances between 0.2 and 0.8, is good. But this is just a rule of thumb, but there are different components that will necessarily have wider linear range than others, and you can absorption of 1.5 will still be acceptable for some.
Yeah, I have a question. I know Megazyme has a starch kit where they actually want the range to be 0.1 to 0.4.
Yeah.
Why would they want a lower absorbance
Again,
compared to that bigger range you're talking about, or the higher absorbance?
well, I'm not sure why Megazyme specifically say 0.1 to 0.4. This is a very narrow range, but it could be that you lose linearity very quickly in this assay. I'm not sure. I'm not familiar with that. Who does it in our lab very common? That would be Amy or Citra, right? The
Yeah.
Megazyme starch.
Yeah. Citrus done it most, but they both have done it, and then Jenny's done it for millet.
Jenny, you remember the assay says 0.1 to
Yeah,
0.4?
That's what it says, yeah.
Okay, yeah, I'm not sure why it's that low. It's very unusual, but could be very unique for that particular assay. Okay. So, yeah?
Just want to answer with all of the
Oh, hold on. Has to be small relative to variation from, yeah, that is correct. And that is correct. So you can be tested. So you measure the same sample multiple times and see if what would be the noise. Sometimes it will give you 0.75 absorption, another time it will give you 0.76, another time it will give you 0.74. Then you will know, oh, okay, my noise is about 0.1 or 0.01. So that is correct, and can be reduced by the use of intermediate concentration. We talked about that. So yes, all of the above. Okay. So this is a very simple interior look to a spectrophotometer. So basically, you have your source of light, and if you're working in the visible range, you would use a tungsten lamp. That is a common lamp. And if you're working in the UV range, it would be a deuterium lamp. And then you have all the light is going through into a monochromator. And so here's your entrance, goes in, gets diffracted, and then exits as a single or very closely related wavelength. And then that one single or closely related wavelength will hit your sample, and transmitted light will hit the detector. And it will be converted from a photon of light to electric signal, and there will be an amplifier of the signal and the readout. So the detector here, most commonly, it's either a phototube or a photomultiplier. So if we look here, a phototube is when you have a cathode and an anode, and the radiation hits the cathode, emits an electron that is picked up by the anode. However, if you want to amplify sensitivity, increase the threshold, so what you would do, or reduce the threshold, so what you do is you do an amplification, so photomultiplier. So what happens here is you have the beam of light hitting the cathode, electron hits a dynode, and more electrons jumps off of that into a second one, and it kind of increases. Number of electrons increases every time it hits a dynode. And by the end, instead of 1 electron, you can see 27 electrons, so the signal is amplified. So what you had in the AA, those of you that did the AA this week, you had a photomultiplier detection in there. Photodiode, we did that in the LC lab. You have your light, and all of the light hits the sample. All of it, before the monochromator. And then the transmitted light hits the monochromator, not hits the monochromator. At this point, you have an array of diodes, we call them. That's why it's called photodiode, because you have an array of diodes. So the array of diodes is going to give you the electrical signal for each wavelength of light. So you will get a simultaneous readout like this. And we talked about spectra before. So the design of the instrument, you can have a single beam. That means you don't have a reference cell. All of your beam hits the sample and gets detected. The transmittance get detected. Or if you have a double beam, that means you have a reference cell. So what happens is the lamp hits here and gets divided. So you'll end up having one beam going to the sample and one beam going to the reference cell. The reference cell will have everything, all the reagents that are in your sample, so basically your blank. So at the same time, you get a reading from the reference cell and a reading from the sample cell. And you get difference in absorption automatically given out as your absorption of the sample. So the reference minus the sample, because here all the light gets transmitted theoretically, and here part of the light gets transmitted. So, but when you don't have a reference cell, you will just use a blank in the place of the sample cell, and you will manually subtract your blank from your sample. Okay. One thing we make note of is when it is a double beam, the radiant power diminishes because the light will be divided in half basically between your sample and cell. That might reduce your sensitivity or having you have a higher threshold. So you would just work with that. This is just an FYI reference table where it shows you that different groups present in different components will absorb light, and that would be the lambda max, or the wavelength at which you get maximum absorbance. And this epsilon here sign is your absorptivity or molecular or molar extinction. So when it's epsilon, it's mostly molar extinction in the molarity. And for each one of those, you will have a specific one, and that's just the resource. Fluorescence spectroscopy, basically in this case, like I said earlier, you need a wavelength for absorption, and then you select a wavelength to monitor emission of light. So in this setup, your spectrophotometer will have the source of radiation, so it will hit your monochromator, and then you'll get your incident beam or incident wavelength at a particular wavelength, and then it hits the sample. The transmittance continue horizontally. At a 90 degrees angle, you position the transmittance to go, not the transmittance, I mean the emission. The emission to go at a 90 degrees angle, and here you have a monochromator again. So you would select the wavelength at which emission occurs. Okay, so that's what gets measured in this case. This doesn't go to a measurement. Here, the P here doesn't go to a measurement. The PF is what goes and gets isolated into particular wavelength and gets detected, and you get the readout. Okay, so just remember that you will have a wavelength at a higher frequency, more energy for absorption, and the emission is always with lower energy because some of the energy is being dissipated as heat. And yeah, that's all. I deleted the slide that you have there with a bunch of equations. Forget about it, it's not important. And that's it. You will have, I'll send you an email with information for next week. Okay, try to come 5 minutes early on Monday to start quiz. Okay. Thank you.